All right, this is AP Calculus BC, and in this video, I'm going to cover section 4.6, which your book calls rectilinear motion. And in this section, really what we're doing are motion problems. And it's just applications of derivatives with motion problems. So we've already been doing some of this, so a lot of this is going to be familiar, but there are a couple of things in here that can be a little bit tricky that I want to make sure we discuss as I go through this video. So the first part of this, we've already talked about the idea that if we have a position function and we take the derivative, it gives us the velocity. If we take the derivative of the velocity, it gives us the acceleration. So that's all very straightforward. The one thing I want to caution you about, many of you in physics have learned kinematics equations that are really easy ways that you can kind of shortcut the process that we're trying to do here. The thing that I want you to keep in mind is I don't want you to shortcut the process, because a lot of those equations that you're using are equations that are derived using things that you're going to do in this section. So finding out where those equations come from is really critical in terms of understanding why they work and how they work. So don't just skip to the shortcut kinematic equations that you know. Try to actually work these out with derivatives as intended. Okay, so here's an example that I want to try to work through. It says the position of a particle is given by this equation. Position is a function of time, and it's t cubed minus 6t squared plus 9t. So part A, very simple. It says find the acceleration at time t. What is the acceleration after 4 seconds? Okay, so remember when we see s, that's going to represent position. So when I take the derivative, I can call this s prime. I could call it f prime. I'm going to call it v for velocity. So my velocity as a function of time is just the derivative of that position. It would be 3t squared minus 12t plus 9. Oops, 12t plus 9. Okay, so very simple. And then to get the acceleration of that, acceleration is the rate of change of the velocity. So that would just be 6t minus 12. So I'm just taking the derivative of that quadratic expression. They asked for the acceleration at time is equal to 4. So the acceleration at time 4, we're just going to plug time 4 into that acceleration function that we have, and we're going to get 12. In this case, it would be meters per second squared. Okay, so very, very simple to do. Now, this said to graph the position, the velocity, and the acceleration functions. I already have the graph here because I wanted to make sure we had a really accurate, clean graph to work off of so that we can discuss the answer for part C. But you can see on this graph, the position function was cubic, the velocity is quadratic, and the acceleration is linear. So it's pretty easy to pick out which is which. Part C, it says, when is the particle speeding up? So speeding up and slowing down, this is going to be the one thing in this section that can trip you up a little bit. And so I want to show you a few different ways that you can figure out speeding up and slowing down. When we have a graph, this is actually pretty easy to do if we're looking at a velocity graph. So remember, speed is the magnitude of velocity. So if I'm just purely looking at the velocity graph and kind of disregard the position and acceleration for a second, if the velocity is getting closer to 0, I'm slowing down. If the velocity is getting further from 0, I'm speeding up, because when I'm getting further from 0, magnitude is increasing. When I'm getting closer to 0, magnitude is decreasing. So you can see on this first interval here, I would be slowing down because the velocity is getting closer to 0. And then on the next interval from 1 to 2, you can see I'm speeding up, and then it starts moving back towards 0, so I'm slowing down, and then on the last interval, it just speeds up the rest of the way. So I'm going to write out my intervals here. So the first one for speeding up, let me go back and look at this graph again, speeding up. So on my graph, when I go through and take a look at the intervals here, remember speeding up was when the velocity was getting further from 0. So that's happening from interval from 1 to 2. And then also over here from time interval from 3 out to 5, since our time interval ends at 5. So we'd be speeding up from 1 to 2, and then also from 3 to 5. Another thing that can come up in these questions is whether or not we should be including the endpoints in these intervals. And that's a debatable topic. You can include them or not include them. It doesn't really matter. And so I don't care which way you write it. the main thing is to understand that when you're looking at a question and the intervals are given, if they include the endpoint, that's okay. So there's a mathematical argument that can be made to justify both including and not including the endpoints. You'll never see a question where you have to decide to include or not include. It'll either be all the endpoints are included or all the endpoints are not included. So just keep that in mind. Okay, and then also here for slowing down, we want to have the intervals where the velocity is getting closer to 0. And you can see the time interval from 0 to 1, which we looked at earlier, and then the time interval from 2 to 3. Okay, so again, either include or don't include the endpoints. It doesn't really matter. Just be consistent with the way that you write it. Okay, so that's one way we can do it, is just looking at the velocity graph. But another way we can do this is to combine the information that we have with the velocity and the acceleration. And to do this, what we really want to be thinking about is vectors. When we think about vectors, think about the direction that a vector points in, if it's positive or negative. So a positive, obviously, or a negative is going to point in opposite directions. So when I'm looking at velocity and acceleration, if those vectors are pointing in the same direction, we're going to be speeding up. If those vectors are pointing in opposite directions, we're going to be slowing down. So that's really the way that I think about this, is from the vector perspective, because the acceleration vector is the rate of change of the velocity vector. So if you graph those side by side, like for example, here's my velocity vector and here's my acceleration vector. Well, if they're pointing in the same direction like that, then you can see that the acceleration is kind of pushing the velocity vector to get longer. If I had an acceleration vector that went in the other direction, you can see it's working against the velocity vector. That's going to make me slow down. So if they point in the same direction, we're speeding up. If they point in opposite directions, we're slowing down. And we can just verify the solutions that we got here on this part C just using the graph. So for example, the time interval from 0 to 1. Notice that the velocity here is positive and the acceleration is negative. So it makes sense that we would be slowing down. On the next time interval from 1 to 2. Well, from 1 to 2, the velocity was negative and the acceleration was negative. So those vectors are pointing in the same direction. We're speeding up. Okay, so that's kind of the general idea behind the thought process of speeding up versus slowing down. If you think of it from a vector perspective, I think it makes perfect sense. If you just try to blindly memorize a rule, it's going to be a little bit harder to remember the rule. Okay, so here's just a summary of that for speeding up and slowing down. So a particle speeding up when obviously its speed or the velocity magnitude is increasing. It's slowing down when the velocity magnitude is decreasing. And here's what we just talked about. It says we're speeding up when velocity acceleration have the same sign, slowing down when they have opposite signs. Okay, so again, think about why that's the case as opposed to just memorizing that statement, and then it'll be a lot easier to remember which is which. Okay, so here's another example that I wanted to talk about. And what we're looking at here, it says the graph below shows the velocity of a particle moving on a coordinate line. And they have a bunch of questions about moving forward, moving back, acceleration, speed, and then constant. So notice that there's not really a lot of information given on this graph. On these types of problems where you're given a graph, what I always like to do is I like to label my graph so that I remember what is this graph displaying. They described it up above, but it's not labeled here on the graph. So this was the velocity graph. So I want to make sure I keep that in my head. And I usually write it on the graph like that. And then that way, every time I look at this graph, I remember this is the velocity graph. Okay, so part A. When does the particle move forward, move backward, speed up, and slow down? So moving forward is just positive velocity. Moving backward is negative velocity. So since we're looking at this velocity graph, anytime our velocity is above the x-axis, or the time axis, I should say, we would be moving forward. Anytime it's below the time axis, we'd be moving backward. So pretty easy to see here for forward and backward. So let me make this a little bit larger so we can fit this. So for forward, we would have the time intervals. And remember, I'm going to do the same thing with the intervals here. I'm not going to include the endpoints, but if you do, it's okay. So I would have the intervals from 0 to 1 and also the interval from 5 to 7. And let's just take a look at the graph and see again why that's the case. From 0 to 1, you can see the velocity is positive, and from 5 to 7, you can see that the velocity is positive there as well. Okay, and then we want to do backward. And same idea. So for backward, I'm going to get the time interval from 1 to 5, and then also the time interval from 7 to 9. Okay, so again, take a look at the graph. You can see that the velocity is negative from 1 to 5, and it's negative from 7 to 9. So now the speeding up and slowing down, we just looked at this type of a question a minute ago. So if I'm going to be speeding up, that means that my velocity should be moving away from the time axis. Well, now just glance at that and you can see we're moving away from the time axis on the interval from 1 to 2. We're moving away from the time axis on the interval from 5 to 6, and we're moving away from the time axis on the interval from 7 to 8. So I actually have 3 intervals here where I'm going to be speeding up. So I had 1 to 2. We've got 5 to 6, and we also have 7 to 8. Okay, and then we're also going to be slowing down on some intervals. And just by process of elimination, I can get most of this, but we have to be careful because there is one interval where our velocity is constant. So slowing down is when the velocity is moving towards the time axis. So obviously from 0 to 1, from 3 to 5, and then from 6 to 7. Okay, now notice we have these time intervals where we're not speeding up or slowing down because the velocity is constant. So keep that in mind. Okay, so for slowing down, I had 0 to 1. I had 3 to 5. And I had the time interval from 6 to 7. Okay, so this, once you understand how to read these graphs, this is really not difficult to do. Part B, it says, when is the particle's acceleration positive, negative, or 0? So positive, negative, or 0, when we're talking about acceleration, remember acceleration is just the slope of the velocity. So you can see we have a negative slope from 0 to 2, we have a positive slope from 3 to 6, and a negative slope from 6 to 8. So that's how I'm going to figure out my acceleration being positive or negative. So we had one interval where it was positive, and that was the time interval 3 to 6. And we had 2 intervals where it was negative, and that would be the time interval from 0 to 2 and the time interval from 6 to 8. And then the last part, it also says when is the acceleration 0? Well, it's 0 on those intervals where the velocity was constant, and that was on the interval from 2 to 3 and the time interval from 8 to 9. Okay, so again, for the 0, remember I'm looking for these horizontal segments here because that means my velocity is constant. All right, so let's look at part C. When does the particle move at its greatest speed? So its greatest speed is going to occur when we're the furthest from 0. Since we don't have a scale on our axis here, it's kind of hard to tell. And whether or not you want to include this point at 0 is debatable. So I'm going to go ahead and include it, but we could also exclude it and say that, you know, time equals 0 is not included in our interval. They didn't really define our interval for us here. So it looks like between 2 and 3 and at time 0, I have about the same speed. So I'm going to say it moves at its greatest speed at time is 0 and also on the time interval from 2 to 3. Okay, so for this last part, it says, when does the particle stand still for more than an instant? And so remember, we need to have a 0 velocity, and we need the velocity to be 0 for more than one moment in time. So looking at this graph, I can see I have a 0 velocity at time 1, time 5, and time 7, but it's never actually an interval of time. It's never more than one particular moment in time. So for this last part, it would just be never. Okay, so let's take a look at what I supplied for you here. So I just gave you some graphs here that give you a general idea. If you're looking at a position curve, what does that mean in terms of speeding up, slowing down? What does it mean in terms of the velocity being positive or negative. What does it mean in terms of the acceleration? So there's different characteristics that you're going to see. So for instance, I'll just go through the first one and you can read through the rest of these on your own. We have this position graph and you can see it's increasing and concave down. So increasing and concave down. So think about what that would mean from a derivative perspective. That means your first derivative is positive. So that means we have a positive velocity. But then the second derivative would be negative. So that means we have a negative acceleration. So I can tell that I'm still moving in the positive direction, but I can also tell that the velocity is decreasing and that I'm slowing down because the acceleration and the velocity would have opposite signs. The first derivative and the second derivative are positive and negative respectively. So that's how you would interpret those. It still goes back to the stuff we were doing back in sections 4.1 through 4.4 when we were talking about increasing, decreasing, concave up, concave down, and all those things. It's just that now we're applying it to position, velocity, and acceleration. All right, so the last thing here is just a little bit of practice. It says the figure shows the graphs of position, velocity, and acceleration. Identify each curve and explain your choices. So what I want you to do is pause the video and think about this for a minute and try to figure out which one should be the position, which one should be the velocity, and which one should be the acceleration. So when you come back, I'll show you the solution for that. Okay, so you have to think about this a little bit, and I'll explain how I came up with these. So I have my position graph being A, I have the velocity graph being C, and I have my acceleration graph, obviously then being graph B. Now, the way I came up with this, you really just start with one and see how they match up. If A is my position graph, notice there's a zero slope there. That means that whichever one is my velocity graph would have to have a value of 0 at that point. And you can see C has a value of 0. So far that matches up. I can also see that for graph A, it's increasing to the left of 0 and it's decreasing to the right of 0. So if C is going to be my velocity graph, it should be positive to the left of 0 and negative to the right of 0. And that's all making sense so far. Now, the last thing I want to check, if A and C are matching up, is B going to match up and be the acceleration graph? So look at the velocity graph now, graph C. So from the left side of the graph up to a little to the left of 0, you can see I've got a velocity that is increasing. That means that my acceleration graph should be positive. And you can see graph B is positive all the way to this point. Those points are matching up. And then on the interval from that point a little to the left of 0, over here a little to the right of 0, you can see that we have points that match up again where the acceleration should be negative. We have all these negative values here matching up with the negative slope that I see on the velocity graph. And then for the last interval, you can see that the acceleration is still going to be, let's see, it switches back to positive, and you can see the velocity graph then starts to increase in value. So it's really just a matter of kind of picking, seeing if things match up, and when they don't match up, then you can rework things from there. But using the 0 points and then the increasing versus decreasing is really the trick to that. And it's just a matter of kind of sorting through it and trying different things until you find the one that works.